take a look at finding a partial fraction decomposition. So on this problem, we have a linear denominator factor and an irreducible quadratic. So what we need to do is we need to make an educated guess on what type of partial fraction this is going to break up into. An irreducible quadratic is a quadratic function or expression that you cannot factor. So the linear one can be represented as an a, unknown numerator, coefficient, over the x plus 5, and the irreducible quadratic is represented with a linear numerator. The general numerator for a irreducible quadratic is a linear form, in this case bx plus c, since we're already to the letter b. All right, we then multiply by the LCD, which is always the first fractions denominator, the one you are doing partial fraction decomposition on. And you need to multiply by this factor on each term on the left and right. With the irreducible, the linear numerator, bx plus c, you need to put parentheses around it because you're going to have to do some distribution in general on that term. Okay, this gets rid of the fractions, leaving us on the left with just 5x squared plus 11x minus 14. And on the right, we can write the a and the x squared plus 3, and the bx plus c and the x plus 5. All right. There are several approaches to finish this problem. What I like to do is smart values. Originally, any linear factor comes with it a domain restriction. Irreducible quadratics don't have domain restrictions, but we can at least, what you do is you let x equal the domain restriction value, and when you plug that in, that'll go, oops, that's not where I meant to put it. That'll go in all the x's, including there. So when I use x equals negative 5, that makes 0. That wipes out this entire second term. And I get 5 times negative 5. Here we probably just worked that all out. So we'd have 5 parentheses negative 5 squared plus 11 times negative 5 minus 14. This is the left side, 56. Negative 5 squared is 25. 25 plus 3 is 28a. And again, that term is 0. So out of this, we can solve for a, and we get a equals 2. Brilliant. Easy to do. Now, if I let x equal 0, I use 0 on irreducible quadratics because when I plug in 0, that gets rid of the b. It'll get rid of other things, but it gets rid of the b. I already know a. That should allow me to find c. So plugging in 0, I would get negative 14 on the left, 3a plus 5c on the right. If I plug in 2 for a, that is negative 14 equals 6 plus 5c. Subtract 6 to the left, and out pops c equals negative 4. Wonderful. Now we just have to get b. You could use just another value, x equals 1, for example. That would look like 5 plus 11 is 16, minus 14 is 2 on the left side. 1 here would be 4a plus 1b, b plus c, times 1 plus 5 is 6. And then we can use the a that we have and the c that we have. And out of this, we should be able to solve for b. That is one approach. Let's finish it. A is 4. 4 times 2 is 8. Plus b minus 4 times 6. Subtract the 8. Divide by the 6. And out pops b equals 3. Another approach would be compare, for example, the x squared coefficients. On the left, we have 5 of the x squareds. On the right, we will have a, the x squareds, and b of the x squareds. That would give us an equation 5 equals a plus b. Knowing a was 2, that is an easier equation to find that b, but it doesn't really matter which way you do it as long as you're able to find it. So there's a method of comparing coefficients that could give you a 3 by 3 system to solve, but these smart values and a dumb value or comparing one coefficient end up a lot easier than solving a 3 by 3 system. Now for the final answer, we want to write our guess as a, 2 over x plus 5 plus bx, 3x plus c minus 4 over x squared plus 3. And this is the partial fraction decomposition of our initial question. All right, I hope this helps.